In this video, we'll continue our discussion of polar integration, finding the volume, and we're just going to set this integral up. I think we've done plenty of practice for some integrals. For the sake of keeping videos short and not exhausting you through so many, because I know these are long, we're just going to set the integral up and stop, and I'll give you an answer, and you can check it if you would like. All right, so notice they give me two z's here. We have z, the first one. Let's go ahead. I'm going to try to make this a little more obvious of what it is. I can factor out a half of those, and I get x squared plus y squared if I factor out the negative half. That is a paraboloid shifted up 10. It's going to be a little wider because of the half, and it's opening down. All right, z equals 2 is just a plane at z equals 2. I need to find, okay, I have that. I would like to find where they intersect, because that's going to give me something. That's that circle right here that we're looking at. So I could just plug in 2 here and start working this out. All I did is set my equations equal because I want to know where they intersect. So what I'm doing, this isn't going to be on the xy plane, but it's like 2 up, but it's going to help us figure it out. All right, so I got negative 8, if I move that 10 over, equals negative 1/2 times x squared plus y squared. If we multiply by negative 2, we get a 16 equals x squared plus y squared. That is the reason we have the circle. This is not at the xy plane. It's a projection onto the xy plane. This circle actually exists when z equals 2. That's where our two functions actually intersect. We can use this, though, to switch to polar. So if we look at here, our r, it's nice and easy, 0 to 4. And then theta, it's nice and easy as well. It's all the way around. So it's 0 to 2 pi. So my volume, if we were going to set it up, I have theta on the outside from 0 to 2 pi. R is just going to go from 0 to 4. It's nice and pretty. And then this is my function right here. So I'm going to plug that in. I got a, that's my top function. And then I'm going to have to subtract the bottom function. So it's going to be this function minus that function. So that is 10 minus 2. So we get an 8 minus 1/2 times x squared plus y squared. Okay, we can replace that, though. So if I subtract my z's, let's make this a little more obvious. If I do, let's call this z1 and z2. If I do, first we got to figure out which one's on top. Let's do that. How we can tell that is just make sure you pick a point in the region. Okay, there's a very easy point here to check. 0, 0. If I plug in 0, 0 here, all right, 0, 0, I get a 10. If I plug a 0, 0 into here, I get a 2. So this tells me this is on top and this is on bottom. You just got to pick a point in the region. That's the important part. It's just pick a region. If I take now this function minus this function, I'm going to get 10 minus 1/2 x squared plus y squared. We can leave that. I'm not going to touch it. Minus 2. Well, that 10 and 2 make an 8. Times that. I can also replace the x squared y squared with r squared. So I'm going to get 8 minus half r squared. All that, if I'm switching to polar, remember I got to add an r, dr, d theta. All right, let's go ahead and multiply that out to make it a little easier for us. Go ahead and rewrite my bounds. Nothing has changed. I'm just going to multiply things out. I got 8r minus 1/2 r cubed dr d theta. I'm going to stop there because that integral is pretty straightforward. We've done some of those already to keep length down. This answer is going to end up being 64 pi. So if you'd like to work it out and check, the hard thing, if you haven't been able to tell, the hard thing is setting these up. Integration is difficult afterwards. It can be, but it's the same methods over and over. The setup's going to be the most difficult part.